The cometary visitor known as 3I divided by Atlas was already extraordinary. Only the third recognized interstellar object across our solar system, it carried with it the ancient fingerprints of another star's nursery. Yet in the silence of deep space, astronomers caught sight of something that should not have been there, an unfamiliar glimmer, a companion-like form that seemed to emerge beside 3I divided by Atlas, as though a secret had been hiding in its wake. Was this merely a trick of distance and dust, or had a new traveler revealed itself, one bound by forces we do not yet understand? Such moments remind us that the universe is never a still painting. It is alive with events unfolding beyond the reach of certainty, asking us to look again and again. Tonight, we embark on a new journey, where the theme of 3I divided by Atlas shocked scientists as a new object emerged beside. It appears not only as a scientific phenomenon, but also as a question that challenges our imagination. If you enjoy this kind of quiet, long-form storytelling, if it helps you learn, focus, or simply relax at the end of a noisy day, take a moment to like the video and subscribe, but only if this space truly brings you peace. And tell me, where are you listening from? Which horizon, which midnight window, which corner of the world do you bring into this shared moment? It's always fascinating to see who's joining us from all around the world. In the hours of observation that followed, scientists began to wonder whether this sudden apparition was only a shard of cometary dust set aglow, or if it was something more deliberate, an echo of matter breaking free, or even a signal of hidden kinship. Subtle flickers of gas, of dust, of radiation seemed to hint at synchronized activity. Spectral analysis whispered of shared chemistry, a possible bond between the newcomer and 3I divided by Atlas itself. And yet, the greatest telescopes, JWST, Hubble, and their ground-based counterparts, offered only fragments, pieces of a puzzle not yet whole. Within those fragments, the imagination of astronomers and dreamers alike began to run. Could this be a cloaked interstellar agent trailing in the comet's dust? Or a relic core, carrying the fossilized chemistry of a long-dead star system? Or perhaps, most audacious of all, a beacon of unknown origin, an artifact designed to observe, hidden in plain sight against the comet's fleeting glow? In the cold, silent expanse beyond Mars, a point of light that has captivated the scientific world. Designated 3I divided by Atlas continues its solitary, hyperbolic plunge through our inner solar system. As the world's most powerful telescopes, from the venerable Hubble to the nascent James Webb, train their gaze upon this third known interstellar visitor, a new, tantalizing mystery has emerged from the depths of the void. Nestled within the faint, ethereal glow of its coma, a shroud of dust and gas stirred to life by our sun's gentle caress, a secondary point has flared into existence. This faint, unexpected luminescence, clinging to the periphery of the comet's primary activity, presents an immediate and profound puzzle. Is this merely a transient clump within the comet's own effluence, a trick of celestial light and shadow? Or could it be something far more significant, an independent traveler, a silent companion hitching a ride on this interstellar stage? From a conservative, methodological standpoint, the most parsimonious explanation is one of simple, chaotic physics. According to current models of cometary outgassing, the nucleus of 3I divided by Atlas, a pristine relic from a star system far beyond our own, is undergoing intense heating. As volatile ices sublimate, they carry with them countless dust particles, creating a turbulent and dynamic cloud. Within this cloud, complex interactions, collisions, electrostatic forces, and the subtle pressure of solar radiation can cause particles to coalesce into temporary, denser knots. These knots would appear as localized bright spots, flaring with sudden intensity before dissipating back into the diffuse background of the coma, a phenomenon well documented in countless other comets that call our own solar system home. This, the scientific consensus suggests, is the most likely scenario, a fleeting illusion of structure, born from the inherent stochasticity of a degassing ice ball. Yet, if this is merely a transient, density fluctuation, why does its photometric signature persist across multiple observational epochs? And why does its relative position suggest a trajectory, subtly, yet distinctly, independent from the chaotic churn of the surrounding dust? This persistent anomaly invites a more promising and consequently more thrilling hypothesis. Perhaps we are not witnessing a simple knot of dust, but the actual physical fragmentation of the interstellar nucleus itself. The immense thermal and tidal stresses imposed by its first ever encounter with a star could have been sufficient to cause a piece of the primordial body to carve away, much like an iceberg shearing from a glacier. This fragment, now a smaller companion, would possess its own, albeit weak, gravitational bond to the primary nucleus and would begin its own, independent, if short-lived, outgassing cycle. This could elegantly explain both the sustained brightness and any potential periodic variations as this newborn microcomet rotates, presenting its active and inactive faces to our watchful instruments. The European Space Agency's dedicated observation handbook for 3I, divided by Atlas, would then serve as a manual for witnessing, in real time, the violent birth of a binary interstellar system. But what if the fragment itself is not a simple shard of ice, but a constituent part with a different, more resilient composition, one that has remained dormant until now? This line of inquiry compels us to consider a third, truly transformative possibility, that this is not a fragment at all, but an independent, co-orbiting object. A companion whose origins are as ancient and mysterious as 3I divided by Atlas itself, now revealed only by the illuminating power of our Sunday. The implications of this are staggering, for it would force a complete rewrite of our understanding of interstellar comet formation and evolution. It suggests that the processes which build planetary systems around other stars are capable of creating complex, multi-body relationships even amongst the smallest, most nomadic of objects. This companion could be a captured asteroid from its home system, a twin nucleus formed from the same collapse of a distant protoplanetary cloud, or something else entirely, a piece of planetary debris from a cataclysm light-years away, now holding within its uncharted chemistry the frozen history of a long-dead star system. Could its seemingly anomalous structure and activity be the key to performing a direct, comparative analysis of primordial matter from two separate, alien sources within a single, captured frame? The confirmation of a true, independent companion would be an unprecedented scientific opportunity, a chance to dissect, for the first time, the multifaceted complexity of an interstellar object. It would provide two data points from the same foreign system, allowing us to compare isotopic ratios, organic compound inventories, and structural properties, thereby opening a window not just onto one world, but onto the fundamental conditions of an entire alien planetary disk. Every piece of data, from the subtle Doppler shift in its reflected light to the specific absorption lines of its volatiles, would be a cipher waiting to be decoded. Yet, to move from speculation to confirmation, we must first answer a more fundamental and deeply geometrical question. Where, precisely, is this enigmatic object in relation to its primary, and what path does it trace through the void? The true nature of this mystery may only be unlocked by first charting its course, by understanding the precise dance between this newfound point of light and the interstellar wanderer it accompanies. For the trajectory it follows will tell us if it is bound by gravity or merely passing through, if it is a moon, a fragment, or a sovereign entity sharing a road through the solar system. And so, we must now turn our gaze from the question of times, what times it is, to the critical puzzle of times, where times it is going, a puzzle, defined by its relative position and its plausible orbit around 3I divided by Atlas. Location does not lie. In the silent, depthless expanse through which the interstellar wanderer, known as 3I divided by Atlas, journeys, every pixel of light, captured by our most powerful instruments, tells a story of motion, mass, and influence. If, amidst the brilliant chaos of its coma, a point of light were found to be displaced, drifting out of phase with the primary nucleus, it would bear the unmistakable signature of an independent orbit, a gravitational whisper of a separate existence. This is the subtle clue that transforms a solitary traveler into a potential system, a single narrative into a complex dialogue between two bodies. The relative position and potential orbit of this new object in relation to 3I divided by Atlas thus becomes the first critical cipher to decode, a puzzle written in the language of celestial mechanics against the velvet backdrop of the void. From the perspective of conventional science, The most parsimonious explanation would be that this point of light is merely a dense, transient clump of outgassing dust, a localized jet of material caught in the act of being sculpted by the solar wind. According to current models of cometary behavior, such features are common. They are born from the volatile and uneven surface of the nucleus, momentarily bright and coherent, before dissolving into the diffuse luminosity of the tail. They are phantoms of the coma, possessing no true orbital independence, merely riding the relentless outflow of solar radiation pressure. Yet, what if this particular point of light exhibits a slight but persistent lag, a minute discrepancy in its angular velocity that cannot be fully accounted for by the simple physics of dust dynamics? Could it be that we are not witnessing a jet, but something far more substantial, held in a delicate, gravitational embrace? This is where the mind is permitted to venture into more speculative realms. One might hypothesize the existence of a binary ice satellite, a fragment of primordial rock and ice, a captured shard from the object's formation in some distant star system, now tracing a tight, looping path within the weak gravitational field of the primary nucleus. It would be a miniature world orbiting a traveler, a moon for a wanderer. An even more exotic possibility presents itself: a light sail glider, an artificial construct designed not to escape the comet, but to use the very radiation pressure that blows the dust tail as a means of propulsion, allowing it to station keep at the periphery of the coma. Such an object could theoretically tack against the solar wind, maintaining a seemingly impossible, fixed position relative to the moving nucleus, using the comet as both a shield and a beacon. But how could we possibly distinguish between a natural satellite and an engineered one, when both could occupy a similar orbit? The fortuitous passage of 3I divided by Atlas through the orbital precinct of Mars in the coming months provides an unprecedented opportunity for empirical resolution. Orbital assets like the Trace Gas Orbiter, the Mars Reconnaissance Orbiter, and Mars Express will be perfectly positioned to conduct multi-angular observations, triangulating the position of any secondary source with a precision unattainable from Earth's vicinity. The object's hyperbolic trajectory and its upcoming perihelion in October 2025 create a predictable clock against which any anomalous motion can be measured. By meticulously analyzing the astrometric data from these platforms, astronomers can begin to separate the absolute motion of the comet from the relative motion of any potential companion, peeling back the layers of apparent movement to reveal the true dynamics at play. Does the fidelity of this impending multi-point observation campaign hold the key to resolving this celestial mystery? Our analysis must therefore proceed through escalating tiers of complexity, each level demanding a greater departure from the conventional. At the first level, the point of light remains a co-moving feature, an ephemeral structure within the coma itself, a trick of the light and dust that will inevitably fade and disperse, leaving the singularity of 3I divided by Atlas unchallenged. This is the null hypothesis, the outcome that requires no new physics. But if the data reveals a consistent phase lag, a slower angular velocity that suggests a loosely bound, dependent orbit, we ascend to the second level of interpretation. Here, the object could be a true satellite, though a transient one, its orbit unstable and destined to be stripped away by tidal forces or solar radiation over time, a temporary moon for a temporary visitor. What gravitational perturbations, then, would be required to maintain such a fragile, quasi-stable configuration? The third and most profound level is reached if the analysis reveals a truly independent trajectory, a velocity vector starkly divergent from that of 3I divided by Atlas. This would no longer be a satellite, but an independent object, an entirely separate interstellar entity that is not orbiting, but merely traveling in a coincidental and proximate path. The implications of such a discovery would be staggering, suggesting either a common origin point from which both were ejected, or an unimaginable density of interstellar debris that two such objects would be found in such close association. The very notion of coincidence would be strained to its breaking point. Is it mere chance, or could it be a deliberate formation, a fleet of sorts, passing through our celestial neighborhood? Ultimately, the meticulous mapping of this relative motion, whether it confirms a satellite or a companion, opens a new frontier in observational technique. It pioneers a method for the micro-tracking of structures within cometary comae, a skill that will be indispensable for future missions aiming to perform high-speed, fly-by sampling of such elusive targets. The risk, of course, is that we find nothing that the anomaly dissipates, leaving us with a solitary, if still fascinating, interstellar comet. But the opportunity is to confirm that 3I divided by Atlas is not alone, that it carries with it a companion, whether a piece of its own home or something else entirely. And if this companion exists, would its own nature not be irrevocably hinted at by the very evidence of its simultaneous appearance? A story told not by one, but by two sets of data, converging on a single, extraordinary truth. In the hushed and perpetual night of space, a realm governed by the silent, immutable laws of physics, the concept of simultaneity is a thread woven into the very fabric of reality. It is a cornerstone of our understanding, a coordinate on the cosmic grid where events are pinned, one to another, by the unflinching arrow of time. Yet, to witness true simultaneity, the emergence of two distinct phenomena within the same fleeting frame of celestial time, is to be presented with a profound narrative, one that challenges the simplicity of a single actor on a solitary stage. The word simultaneous here implies not just a shared moment, but a shared origin, a choreography so precise it suggests a single director, even as the performers reveal themselves to be fundamentally different in nature. From the dark, frigated heart of the interstellar wanderer, 3I divided by Atlas, data now suggests that two entities arose. One, a beacon of nascent light, a fountain of volatile gases ignited by the distant sun. The other, a more enigmatic presence, a reflector, a passive mirror whose gleam is but a borrowed echo. They ascended together, these twin moons, one shining, one reflecting, like two actors stepping onto the dusty stage of the inner solar system, their entrance perfectly timed, their roles yet to be deciphered. The evidence for this extraordinary duet was captured not by a single, lonely eye, but by a coordinated symphony of the world's most powerful observatories. The Hubble Space Telescope, in its July 2025 observational window, did not merely photograph a comet. It dissected the coma, that hazy shroud of gas and dust, and revealed within it a structure of arresting complexity, a teardrop, a morphology that speaks of forces in tension, of a flow disrupted not by the simple, predictable jets of sublimating ice, but by something more. This was the first clue, the anomalous shape that refused to conform to the elegant, yet perhaps overly simplistic, models of cometary activity. This singular snapshot, however, would have remained a mere curiosity, an unresolved question in the archives, were it not for the densely packed observational schedule maintained by the fleets of ESA and NASA, a testament to human coordination in the face of the cosmic unknown. The Trace Gas Orbiter and the Mars Reconnaissance Orbiter, sentinels at the Red Planet, turned their instruments outward, while a global network of ground-based telescopes swiveled their dishes and mirrors in a unified, silent ballet. As chronicled in the meticulous reports of Space.com, this created a continuous, unbroken stream of data, a cinematic reel of the comet's journey, frame by precious frame. It was this very continuity, this relentless surveillance, that provided the temporal platform necessary to capture an event defined by its synchronicity, to prove that what was witnessed was not a trick of the light or a staggered sequence, but a true simultaneous emergence. At the first level of interpretation, the mainstream scientific explanation offers a compelling, almost elegant, solution. According to current models of cometary physics, a singular, massive outburst could indeed produce the illusion of duality. A violent release of pressurized volatiles from a subsurface cavity, a cataclysm on a miniature scale, could eject a cloud of pristine, highly reflective ice crystals alongside a separate, more diffuse cloud of gas that would fluoresce under the solar wind. The Doppler effect, measured in the subtle shifts of the hydrogen line and other molecular signatures, could, in this scenario, account for slight variations in the apparent position and velocity of these two components, creating the signature of separate sources in the data. The laws of physics, as we understand them in the context of planetary science, provide a complete and self-contained toolkit for this analysis. The simultaneous flash, then, is not a mystery but a consequence, a single cause, giving rise to two distinct visual effects, a single note from a comet's interior resonating into two different frequencies of light. But does a singular outburst truly account for the precise, sustained separation of these two luminous signatures, a separation maintained not for a moment, but for days on end? The teardrop morphology observed by Hubble suggests a shearing, a dynamic interaction between two distinct bodies of material moving at potentially different velocities, a complexity that a single point source explosion would struggle to produce with such clean, persistent duality. This initial rational hypothesis, while satisfying in its parsimony, begins to strain against the weight of the observed data, inviting us to consider a second, more intricate level of complexity. For the narrative deepens when we move beyond the initial flash and examine the subsequent dance of these two entities over the ensuing hours and days. The data reveals a more subtle, yet far more telling, pattern. The two sources of light did not fade in unison. Instead, they exhibited a distinct phase lag, a rhythmic counterpoint where one brightened as the other dimmed, their intensities shifting out of sync over a cycle of hours and then days. This is the second level of the anomaly, a behavior that pushes beyond the explanatory power of a single, cataclysmic event. The mainstream explanation might invoke the rotational dynamics of the nucleus. As the comet spins, different facets, each with unique compositional properties and levels of insulation, are presented to the sunday. One source could be a primary jet, active when its source region faces the solar wind, while the other could be a secondary vent, lagging behind by the comet's rotational period. The outgassing patterns of 67P divided by Churyumov-Gerasimenko, as meticulously documented by the Rosetta mission, provide a rich library of such complex, rotationally driven activity. The phase lag, in this view, is a simple clock, its hands the rising and falling luminance of the two sources, ticking to the rhythm of the comet's spin. However, if this were merely a rotational effect, why would the phase relationship between the two sources itself appear to evolve? The lag stretching and compressing in a manner that defies the predictable mechanics of a solid body's spin? The very nature of their asynchronous brightening suggests not just a temporal offset, but a fundamental independence in their energy sources, a disconnect that implies two separate engines driving the two separate lights. Could it be that we are not witnessing the episodic venting of a single body, but the synchronized activity of two? This leads us to the precipice of the third and most profound level of interpretation, where the data presents its most stark and challenging face. Here, one of the two sources, the reflector, maintained a remarkably steady brightness, a constant, unwavering gleam amidst the stochastic fury of the cometary environment. Its companion, the emitter, by contrast, fluctuated wildly, pulsing and fading with the chaotic rhythm of volatile release. This is the core of the mystery, a pair of objects, born of the same moment, occupying the same volume of space, yet behaving as if governed by entirely different sets of physical laws. The steady source hints at an object with significant structural integrity, perhaps a large, cohesive fragment with a stable, reflective surface, its albedo, unchanging because its nature is solid, permanent. The fluctuating source is the quintessential comet, a transient cloud of gas and dust, its life a brief, brilliant dance of sublimation and dissipation. The implications of this tripartite revelation, the simultaneity, the phase lag, the divergent nature, are as profound for our methods as they are for our theories. The technical synchrony of multi-platform observatories, the exquisite timing that linked Hubble's gaze with the orbital perspectives of TGO and MRO, has transformed our scientific infrastructure from a collection of individual telescopes into a single, coherent instrument, a multi-camera setup directed by an unseen cosmic director, capturing a blockbuster film of an interstellar comet. This coordinated effort did not merely observe an event, it documented a relationship, proving the connection and the distinction between the two actors in a single, undeniable sequence. It is a methodology that will now define the future of time-domain astronomy, turning the entire Earth-Mars system into a single, vast interferometer aimed at the dynamic theatre of the sky. Yet, for all this technological prowess, the fundamental question remains, echoing in the silent spaces between the data points. If these are two separate entities, two distinct bodies that emerged in perfect concert from the darkness, What does this say about the internal structure of 3I divided by Atlas? What cataclysm, what quiet fragmentation, what unknown process could give birth to twins of such disparate character at the same precise instant? The simultaneous emergence of a stable reflective body and a volatile luminous cloud suggests a heterogeneity and a trigger mechanism so finely tuned it borders on the orchestrated. We are left to ponder the architecture of this visitor from another star, an architecture that appears to be far more complex and far more fragile than any simple ball of icy rubble. The very event that brought them forth must have been one of exquisite precision, a fracture along a preordained plane, a release of something that was waiting, poised, within the deep, cold interior. And so, as the twin moons continue their journey, one shining with its own borrowed light, the other reflecting a sun that is not its own, we are compelled to ask the question that will inevitably guide our next observation, our next calculation, our next foray into the unknown. Asterisk, asterisk, could the steady, reflective companion be not a mere fragment, ejected from the main body of 3I divided by Atlas, but an independent object that has, until this moment, been travelling alongside it, hidden within its coma, revealed only now by this peculiar and synchronized activity? Asterisk, asterisk, the void between stars, often imagined as an absolute emptiness, is in truth a deep and resonant ocean. It is an expanse where the faintest whispers of creation are carried on currents of gravity and light, a realm where the silence is so profound that even the passage of a solitary, icy voyager becomes a seismic event in the hushed auditorium of our telescopes. We have given this first confirmed traveller a name 3I divided by Atlas, a designation that belies its profound nature, marking it as an ambassador from a system whose sun is alien to our own. Its hyperbolic trajectory, a razor-sharp arc defying the closed ellipses of our native comets, confirmed its interstellar origin, a moment that recalibrated our understanding of the cosmos, from a collection of isolated systems to a potentially interconnected archipelago. Now, as this primordial fragment from a distant stellar cradle continues its inexorable journey out of our system, a new point of light has emerged in its vicinity, a faint glimmer in the cosmic wake. This nascent spark, this ephemeral datum, presents us with a fundamental and branching question, a taxonomic dilemma that will dictate the very lens through which we interpret all subsequent phenomena. Is this a mere fragment, a tiny shard, cast off from the main body of 3I divided by Atlas, or is it an entirely independent entity, a second wanderer that has, by some inconceivable coincidence, chosen a parallel path through our celestial neighbourhood? The answer to this question of origin, this root and branch divergence, is the master key that unlocks two entirely different narratives of cosmic evolution. On one hand, the mainstream scientific explanation, grounded in the well-understood mechanics of cometary decay, offers a plausible and parsimonious scenario. According to current models, as a comet like 3I divided by Atlas ventures closer to the warmth of a star, its ices, a frozen repository of water, carbon monoxide, and methane, begin to sublimate. This process is not always a gentle, uniform deflation. It can be a violent jetting activity that fractures weaker structures on the nucleus. The resulting debris field, a cloud of dust and small particles, can be shepherded by solar radiation pressure, forming the characteristic coma and tail. The newly detected object could simply be a larger-than-average chunk of this ejecta, a piece of the primordial iceberg that has been recently liberated and is now briefly illuminated by the sun, destined to soon dissipate into the undifferentiated background dust of the interplanetary medium. This is a familiar, almost comforting, spectacle within our own solar system. Yet, the very strangeness of 3I divided by Atlas itself gives us pause and invites a more audacious, speculative hypothesis. What if this is not a child of the comet, but a fellow traveller? The trajectory of 3I divided by Atlas is a path carved through the galactic disk over millions of years, a path that could have intersected with other, smaller nomadic bodies. Could this new object be a relic from the same ancient protoplanetary chaos that spawned 3I divided by Atlas, a fragment that has journeyed in loose association across the light years, a cosmic consort finally revealing itself in the glare of our sun? Or perhaps it is something far more solitary, a small, independent interloper, a mere pebble on the galactic scale, whose path has, through the indifferent calculus of orbital mechanics, momentarily converged with that of the larger visitor, creating a fleeting and profound illusion of kinship in the immense isolation of space. The distinction is not merely semantic. It is the difference between witnessing the shedding of a skin and witnessing a chance meeting of two strangers in the night. Could the universe, in its profound vastness, be so densely woven with such wayfarers that their paths routinely cross, and we, with our limited gaze, are only now beginning to perceive the traffic? The resolution of this enigma hinges upon a golden opportunity, a celestial ballet meticulously documented by a coordinated armada of our robotic sentinels. NASA and ESA have unequivocally classified 3I divided by Atlas as an interstellar object, its orbit an open hyperbola that confirms its extrastellar provenance. As reported by the Associated Press and detailed in publications like BBC Sky at Night, a fleet of orbiters around Mars, the Mars Reconnaissance Orbiter, MAVEN, and the Trace Gas Orbiter, among them, are poised to conduct an unprecedented observation campaign during the object's perihelion passage. This close approach to the Sun is the crucible of activity for a comet, but it is also the optimal moment for precise astrometry. By measuring the parallax, the slight shift in the object's apparent position against the background stars, as viewed from different locations, such as Earth and Mars, and by tracking its angular velocity with exquisite precision, scientists can construct a definitive three-dimensional map of its movement. A true fragment, gravitationally bound to 3I divided by Atlas, even loosely, would share its trajectory, its motion a mere echo of the primary body. An independent object, however, would possess its own unique orbital energy and vector, a signature that would become starkly apparent under such intense scrutiny. The very geometry of our solar system, and the machines we have placed within it, thus become the instruments for solving a cosmic mystery. But what subtle deviations in motion, what minute differences in velocity, would be required to distinguish a sibling from a stranger in this dark and boundless sea? To comprehend the full spectrum of possibilities, we must consider a hierarchy of hypotheses, each ascending in scale and implication. The first and most conservative level posits the object as a small, cohesive particle, a compact agglomeration of dust and ice, recently ejected from 3I divided by Atlas. Such a fragment would be a transient phenomenon, its brief brilliance snuffed out as its volatile components rapidly sublimate in the solar wind, dissolving back into the anonymity of the cosmic backdrop within days or weeks. It would be a footnote in the life of the comet, a fleeting spark in its coma. The second level elevates the object to a more substantial fragment, a piece on the scale of meters to tens of meters. An object of this size could maintain its structural integrity for a longer duration, remaining as a persistent point source for several weeks, its spectrum potentially revealing differences in composition from the main nucleus, a pocket of purer ice or a denser agglomeration of silicate dust, offering a glimpse into the layered heterogeneity of the interstellar visitor's core. Yet, even this substantial piece would ultimately remain within the gravitational and radiative sphere of influence of 3I divided by Atlas, its fate tied to that of its parent. It is the third and most profound level of hypothesis that truly reconfigures our understanding. This scenario proposes that the new object is entirely independent, a sovereign entity navigating the solar system under its own power, so to speak. Its trajectory would not merely be similar to that of 3I divided by Atlas, it would be a parallel path, one that allows it to pass through the diffuse cloud of dust and gas surrounding the comet without being of it. The critical evidence would be its movement beyond this region of influence, its velocity vector decisively diverging from the hyperbolic arc of 3I divided by Atlas as it continues its solitary journey back into the interstellar deep. This is no longer a question of cometary fragmentation, but of a second, distinct sample of material from beyond our solar system appearing, as if on cue, in our observational crosshairs. The implications of such a confirmation are staggering, for it would suggest that the galaxy is not merely sprinkled with the occasional rare visitor, but is in fact teeming with a population of unseen, nomadic objects. If this is not a fragment, but a peer, then what does this imply about the density of interstellar material silently passing through our celestial sphere, unseen and undetected until one chances to fly so close. The consequences of this determination ripple outward, touching the very core of astrobiology and planetary science. Should the object prove to be independent, we are presented with an unparalleled opportunity. Two interstellar samples, captured within the same field of view, originating from two entirely different stellar nurseries, we could, for the first time, perform a comparative analysis of pre-planetary matter from disparate corners of the galaxy. By studying their spectroscopic signatures, the ratios of deuterium to hydrogen, the abundance of complex organic molecules, the crystalline structure of their silicates, we could ask fundamental questions. Is the recipe for planet formation universal, following a strict cosmic chemistry, or does each stellar system imprint a unique signature upon its children, a chemical dialect specific to its birthplace? The presence of 3I divided by Atlas offered us a single data point, a solitary letter from an unknown alphabet. The confirmation of a second, independent object would provide a second letter, the beginning of a lexicon. It would allow us to move from speculation about a single alien world to the first principles of a comparative exoplanetology. But are we prepared to read what these twin messengers have to say, and what profound truths about our own solar system's place in the galactic tapestry might they reveal? This initial mystery of origin, however, is merely the prelude to a far more complex and dynamic interaction, one governed by the most fundamental and pervasive force in the universe. For if these are two distinct entities, their proximity is not a mere static tableau, it is a dynamic relationship, a silent, invisible dialogue conducted across the void. The resolution of their individual paths is only the beginning, for it leads us to an even deeper enigma, one that probes the subtle architecture of space-time itself and the forces that sculpt the journeys of solitary voyagers through the lightless gulfs between the stars. What unseen threads of gravity might be weaving their paths together, and what secrets of mass and density could this silent celestial dance reveal? The cosmos, in its grand and silent choreography, operates on a scale of forces that defy human intuition. We perceive gravity as the great architect of the universe, sculpting galaxies and binding stars in vast, millennial-long orbits. Yet, there exists a realm where this fundamental force is reduced to the faintest of whispers, a domain where the gravitational constant becomes a mere suggestion rather than a command. It is here, in the tenuous space between a wandering interstellar object and the microscopic particles that might accompany it, that we find a theatre for the most delicate of ballets. The gravitational interaction between the interstellar comet 3I divided by Atlas and its hypothetical new companion is not a story of grand captures or cataclysmic collisions. It is a narrative written in the language of subtle perturbations, where the weakness of the bond is precisely what allows for the emergence of transient, almost ghostly, trajectories. Gravity may be weak, but it is never zero, and that is where the most fragile of orbits are born. According to current models of cometary science, an interstellar visitor, like 3I divided by Atlas, having been forged in the crucible of a distant star system, would likely be accompanied by a cloud of debris, a shroud of dust, and ice particles liberated from its nucleus by the gentle, unceasing pressure of stellar radiation. These particles, tiny and insignificant on their own, become celestial subjects to the comet's minuscule gravitational field. The mainstream explanation posits a simple, almost passive relationship. These motes of dust and ice are mere passengers, their paths dictated primarily by the solar wind and radiation pressure, with the comet's gravity playing a negligible role in their ultimate dispersion into the void. They are like smoke particles in a gentle breeze, their individual motions overwhelmed by the flow of the interplanetary medium, their fate sealed not by the pull of their parent body, but by the push of the Sunday. But what if, within this chaotic dispersal, there exists a more intricate hierarchy of allegiance? Could it be that for a select few of these particles, the weak gravitational whisper of 3I divided by Atlas creates a temporary sanctuary, a fleeting pocket of order within the interstellar chaos? This introduces the speculative concept of the microgravity dance, a hypothetical waltz where a dust particle, caught in the delicate balance between solar radiation and the comet's feeble pull, executes a single, graceful loop around the visitor, before being irrevocably swept away by the solar gale. It is a dance of ephemeral loyalty, a final, elegant bow before being cast back into the anonymity of the galactic wind. If such a phenomenon were to occur, what subtle signatures would it imprint upon the comet's extended coma? And would our current instruments be sensitive enough to discern this minute choreography from the background noise of simple particle outflow? The evidence gathered thus far, primarily from the vigilant eyes of the Hubble Space Telescope and corroborated by deep space radar analyses, paints a picture that both constrains and deepens this mystery. Early conjectures, fueled by the object's interstellar nature, envisioned a substantial nucleus, perhaps capable of holding a significant gravitational sway over a vast region of space. The data, however, suggest a different reality. The nucleus of 3I divided by Atlas appears to be smaller and denser than initially presumed. Crucially, and in stark contrast to the perplexing non-gravitational acceleration observed in its predecessor, Oumuamua, 3I divided by Atlas has not exhibited any strong, anomalous thrust that would suggest outgassing powerful enough to substantially alter its course. This absence is profoundly telling. It implies a more consolidated, perhaps older, and less volatile rich core, whose gravitational influence is both pure in its manifestation and intensely localized. This very density allows us to calculate its Hill sphere, the region of space where its gravity dominates that of the Sun, and we find it to be vanishingly small, a mere pockmark on the face of the solar system. Could this compact nature be the key to understanding a unique class of gravitational interactions, one where influence is not a function of sheer mass, but of density and proximity on a microscopic scale? From this foundation of observation and estimation, we can begin to construct a layered hypothesis, a taxonomy of gravitational engagement between the comet and its potential entourage, each level representing a deeper and more complex bond. The first and most basic level is one of negligible interaction, where particles are simply carried along by the flow of gas emanating from the nucleus, their paths utterly dictated by hydrodynamic forces far stronger than the comet's gravitational whisper. These are the lost children of the coma. Their trajectories are a testament to the overwhelming power of radiative and gaseous propulsion over the subtle call of mass. Yet, if we ascend to a second level of complexity, we encounter the phenomenon of temporary capture. Here, the initial conditions of a particle's ejection, its velocity, its angle, its composition, align in just the right way to allow the comet's gravity to briefly seize control. For a handful of hours, or perhaps a few precious days, this microscopic satellite enters a transient orbit, a handful of chaotic loops around the nucleus, before the subtle, cumulative nudges from solar radiation and tidal forces inevitably pull it away, breaking the fragile bond. This is not a permanent capture, but a momentary arrest in the particle's journey into oblivion. What chaotic dynamics govern which particles are granted this temporary reprieve? And could the statistical distribution of these brief captures reveal hidden fissures or density variations on the comet's surface from which they originated? The third and most profound level of this hypothetical interaction is the emergence of a short-term orbital resonance, a gravitational sleight of hand that conjures a horseshoe orbit from the void. In this rarefied state, a particle does not simply orbit the comet. Instead, it and the comet engage in a delicate mutual dance around the sunday. The particle, drifting slightly faster or slower in its solar orbit, approaches the comet from behind or ahead. Rather than a simple flyby, the comet's gravity gently alters its path, causing it to fall into an orbit that, from the comet's perspective, traces a horseshoe-shaped path. It approaches, swings around in a wide, lazy arc without ever completing a full orbit, and then recedes back along the path it came. This is a phenomenon of exquisite fragility, known to occur with some asteroids near Earth, but never before contemplated in the context of a comet and its own microscopic dust. It represents the pinnacle of weak, gravitational influence, a coordinated motion that exists only because the primary force, the Sun's gravity, is so dominant and uniform. Does the existence of such a complex orbital dynamic, however fleeting, suggest that 3I divided by Atlas, in its solitary journey, creates a temporary, miniature planetary system in its wake? A system whose laws are written in the subtle language of three-body problems and resonant frequencies. The implications of understanding these microscopic interactions extend far beyond the academic curiosity of celestial mechanics. To comprehend the subtle scattering of matter in the weak gravitational field of an interstellar comet is to learn the language of cosmic contamination and information transfer. As these visitors slice through our solar system, they act as natural probes, their dust and gas interacting with the solar wind and the interplanetary magnetic field in ways that are unique to their origin. By refining our models of how material is gravitationally teased away from the nucleus and then scattered, we can better predict the flux and distribution of genuine interstellar dust within our own celestial neighborhood. This is not merely about charting the path of a single comet. It is about calibrating our instruments and our intellect for the next visitor and the one after that. It is about understanding the very medium through which our solar system plows and the microscopic, gravitationally influenced debris that might be the only physical samples we ever obtain from another star. But if the dance of dust around 3I divided by Atlas is so subtle, governed by a gravity that is barely there, how then do we explain the more forceful, the more visible, and the more erratic behaviors that seem to connect the comet's nucleus to its surrounding shroud? For the true mystery may not lie in the quiet tug of gravity, but in the sudden, punctuated bursts of activity that hint at a deeper, more volatile connection. This leads us to the next enigma, one that moves from the silent pull of mass to the active voice of energy, the flickering of gas, dust, and radiation, the signs of a binding link within the comet's very activity. If two distant sources of light flicker in perfect unison across the void, it suggests a rhythm not of independent hearts, but of a single, shared breath. This is the enigmatic proposition that now confronts us as we turn our gaze toward the interstellar wanderer, 3I divided by Atlas. Its journey from the depths of interstellar space into the warming embrace of our sun was a spectacle in itself, but within that spectacle lies a subtler, more profound cadence. The official chronicles from the watchtowers of ESA and NASA describe a comet exhibiting typical activity, the predictable outgassing of ices as solar radiation delivers its energizing touch. The scientific summaries tell a familiar tale of volatile ices, primarily water and carbon dioxide, sublimating in increasing quantities as the comet arcs ever closer to the sun, creating the very conditions necessary for the observed, rhythmic, brightening, and dimming. Yet, what if this predictable narrative of heat and vapor conceals a deeper, more intricate machinery at work? One could posit a purely mechanical explanation, a switch engine, governed by the fundamental physics of thermodynamics. Imagine a subsurface reservoir of frozen carbon dioxide, a layer of dry ice nestled within the comet's dark, porous nucleus. As the comet rotates, this reservoir is alternately exposed to the raw glare of the sun and plunged into the profound cold of its own shadow. In the light, the CO2 ice sublimates with immense force, bursting through weak points in the overlying crust to create jets of gas and dust that scatter sunlight, causing the comet to brighten the on state of the switch. In the shadow, the engine cools, the pressure subsides, the jets quiet, and the comet dims the off state. This would be a simple, elegant, and self-regulating clockwork, its rhythm dictated solely by the spin of the celestial body. But does such a straightforward mechanism account for the potential of a shared, synchronized rhythm observed between the main nucleus and a fragment that has broken away, as if both are still connected by an invisible, thermodynamic umbilical cord? This leads us to the first and most intimate level of this cosmic synchrony: synchronized brightness variation. Here, a fragment, recently carved from the primary nucleus, continues to brighten and dim in perfect lockstep with its parent. The mainstream scientific explanation would invoke a profound similarity in initial conditions. The fragment, having originated from deep within the parent body, would possess an identical composition and internal structure. It would be a chip off the old block, quite literally, and thus, when subjected to the same solar flux, its internal switch engine of CO2 ice would activate with the same inherent rhythm. Their rotation periods, inherited from their shared past, would be nearly identical, forcing their day-night cycles, and thus their outgassing pulses, into a natural harmony. They are two clocks, built from the same materials and wound by the same hand, ticking together in the void. Yet, one must wonder, could such perfect synchronization persist amidst the chaotic forces of separation, the subtle differences in their new thermal environments, and the inevitable perturbations of their individual orbits? Or does this perfect unison hint at a connection that transcends mere similarity, a resonant coupling, perhaps, that operates through the very fabric of space-time itself, a concept that challenges our very understanding of locality and independent existence? The plot, however, thickens with the introduction of the second level, a slight phase lag. In this more complex scenario, the fragment still follows the same rhythmic pattern of brightening as the parent body, but it does so a fraction of a flax. Rotation later, like an echo returning from a distant canyon. The conventional analysis points unequivocally to a thermal lag. A smaller fragment, with a lower mass to surface area ratio, would heat up and cool down more rapidly than its larger, more thermally inert parent. While their internal clocks are set to the same fundamental period, the smaller body's response to the solar trigger is simply faster. The time delay between the peak brightness of the parent and the peak brightness of the fragment becomes a direct measurement of their relative thermal inertia. This phase shift is not a sign of a broken connection, but rather a confirmation of it, providing a wealth of data about the fragment's physical properties. It is the predictable behavior of two identical machines, one built on a smaller, more responsive scale. But what if this lag is not a simple function of size, but a manifestation of a deeper, more complex energy transfer between the two bodies, a subtle interplay of fields we have yet to quantify, where the larger body dictates a rhythm that the smaller is compelled to follow, not out of independent function, but out of a fundamental, subspatial dependency? The final, and most disruptive, level of this phenomenon is the complete phase opposition. Here, the correlation between the two objects remains, but it is inverted. When the parent body is at its brightest, the fragment is at its dimmest, and vice versa. This can no longer be explained by a simple thermal lag or shared rotation. The mainstream model would struggle, perhaps proposing a catastrophic reconfiguration of the fragment's internal structure. A violent separation event could have exposed a radically different surface on the fragment, one where the active, CO2-rich switch engine terrain is located on the hemisphere opposite to that of the parent. Thus, when one face is sunward and active, the other's active face is turned away, creating an anti-phase relationship. It is a contrived, yet physically possible, explanation born of chaos. However, does this compellingly simple geological accident truly account for such a precise and sustained opposition? Or could this be the signature of a truly independent thermal structure, one that operates on its own principles, suggesting that the fragment is not merely a piece of the whole, but an entity that has developed, or perhaps always possessed, its own unique and internally resonant switch engine, challenging our very definition of what constitutes a singular cometary body? Thus, the simple act of measuring this rhythmic, brightening this cosmic on, and switching, transcends mere light curve analysis. It becomes a form of remote diagnostics, a way to take the electrocardiogram of a celestial body light years from our finest instruments. The precise shape, amplitude, and phase of these pulses can reveal the porosity, the internal layering, the structural integrity, and the volatile distribution within these interstellar visitors without ever needing to land a probe. The flicker of light becomes a whisper, telling tales of the object's hidden interior. But what deeper secrets might this diagnostic tool uncover if we were to listen not just to the rhythm of one heart, but to the harmonic relationship between two? Could the comparative EKG of 3I divided by Atlas and its potential companion reveal a shared biological, or rather, geological lineage that points to a common point of origin in the vast and uncharted galactic disk? This very question compels us to look beyond the mere rhythm of their light and to delve into the very substance of their being. For if two objects share a synchronized pulse, might they not also share a common chemical soul, a spectral signature written in the light they emit? The flickering rhythm has guided our inquiry to the threshold of a deeper mystery, one that lies not in the timing of their breath, but in the composition of their exhaled vapors. The logical step in this forensic astronomy is to dissect the spectrum of their light, to search for the elemental and molecular fingerprints that could bind them together in a shared history far from our own solar system. What would it mean if the spectral lines of 3 are divided by Atlas and this new, rhythmically linked object were to prove not just similar, but virtually identical, a match forged not in the diverse crucible of a protoplanetary disk, but in the isolated nursery of another star? The spectrum is the chemical birth certificate of a celestial body, a unique identifier etched into the very fabric of light itself. When we train our most powerful instruments upon a distant point of light, we are not merely measuring brightness, we are deciphering a complex narrative of cosmic chemistry, written in the silent language of absorption and emission lines. A match in spectral signatures implies a shared origin, a common lineage written in the atomic and molecular transitions of matter. A divergence, however, tells a different story altogether, a tale of separate births, different environments, and perhaps fundamentally altered destinies. It is within this delicate interplay of spectral lines, these faint whispers from the void, that we seek to understand the profound connection, or lack thereof, between the first known interstellar visitor, 3I divided by Atlas, and this new enigmatic object now drifting through our celestial neighborhood. Could the light they emit, and the light they absorb, reveal a shared genesis, or are we witnessing the first notes of a complex interstellar duet? According to current models of planetary system formation, the chaotic protoplanetary disk that swirls around a young star is a cosmic crucible, forging a diverse population of bodies from a common reservoir of gas and dust. The chemical composition of this primordial cloud, imprinted with the nucleosynthetic fingerprints of long-dead stars, becomes the foundational palette for everything that forms within it. Consequently, objects born from the same disk are expected to carry a familial resemblance in their spectral features, specific ratios of water ice to carbon dioxide, characteristic isotopic abundances, and a predictable suite of organic compounds. The James Webb Space Telescope, with its unparalleled infrared sensitivity, has become our premier instrument for conducting this precise chemical archaeology, tracing the faint signatures of molecules like H2O and CO2 across the galaxy. If this new object is sufficiently bright, a meticulous comparative analysis of the relative strengths and shapes of these spectral lines between it and 3I divided by Atlas would serve as the most critical test for a common origin, a direct probe into their shared or separate pasts. Yet, what if the spectral narrative we uncover is not one of simple familial resemblance, but something far more evocative, something that hints at a process not yet fully understood? We might envision, in a speculative leap, the detection of an anomalous emission band, a broad, complex feature in the infrared that does not correspond to any simple mineral or common ices. This could be interpreted as the spectral flavor of a long-vanished protoplanetary disk, a specific and complex mixture of polycyclic, aromatic hydrocarbons and prebiotic organics that was unique to that one stellar nursery. This would not be a simple ingredient list, but rather the ghostly impression of a specific cosmic kitchen, whose recipe was replicated only in that one place and time. The presence of such a unique and complex spectral signature, shared between two interstellar objects, would be a coincidence of such staggering improbability that it would force a radical re-evaluation of their journey. But does our current understanding of chemistry and physics even allow for such a distinct and persistent spectral fingerprint to survive the harsh radiation and cosmic rays of interstellar space for millions of years? At the first level of interpretation, we may find a spectral match of such striking fidelity that the conclusion appears inescapable. The deep absorption troughs of water ice at 1.5, 2, and 3 micrometers, the sharp vibrational bands of carbon dioxide near 4.27 micrometers, and even the subtle overtones of more complex molecules would align with a precision that defies chance. The relative abundances, the ratios of deuterium to hydrogen in the ices, the fine structure of the silicate, features all would point to a single, shared source material. In this scenario, the new object would not merely be a cousin to 3I divided by Atlas. It would be a direct fragment, a piece shorn from the same parent body in some ancient cataclysm, now following a similar, yet diverging, path through the galaxy. It would be a compelling confirmation that interstellar objects can be generated in familial groups, perhaps from the violent disintegration of a larger planetesimal in a distant system. Yet, if they are truly fragments from a single disruption event, why do their observed trajectories, when traced back, not point to a single convergent point in space and time with greater certainty? The second level of analysis presents a more nuanced and perhaps more intriguing possibility: a near-perfect spectral match, but with subtle, telling differences. The core features are all present, confirming a shared chemical heritage, yet superimposed upon them are the marks of distinct personal histories. One object might show a stronger UV radiation reddening effect, a spectral slope indicative of prolonged exposure to the harsh photon flux of a star different from our own, or perhaps the relentless bombardment of galactic cosmic rays in the isolated darkness. The other might exhibit spectral signatures of recent surface activity, a localized outgassing of carbon monoxide that has subtly altered the composition of its surface ices, or a thermal metamorphosis that has caused the crystallization of amorphous ice, a process that requires a specific and recent thermal pulse. These would not be differences in origin, but rather divergences in experience. They are the spectral scars and weathering that record their individual journeys through the interstellar medium. They are twins, separated at birth, each bearing the unique wrinkles and weathering of their own solitary voyages. But what specific stellar encounter, or what internal geological process, could impart such a distinct and localized thermal alteration without completely erasing the underlying familial spectral signature? It is the third level, however, that opens the door to the truly profound and the deeply mysterious, a spectrum of stark anomaly. Imagine pointing the instruments of the JWST at this new visitor and finding a chemical landscape utterly alien to that of 3I divided by Atlas. Where 3I divided by Atlas showed the familiar bands of water and CO2, this object might display a surface dominated by nitrogen, ice, or vast plains of carbon monoxide with only trace amounts of water. Its silicate features might indicate a formation in an environment extraordinarily rich in carbon, or perhaps devoid of certain refractory elements common in our own solar system. This would not be a fragment. This would be an independent entity, a second, completely unrelated messenger from the vast diversity of galactic planetary systems. Its anomalous spectrum would be a direct sample of the chemical heterogeneity of the galaxy, providing our first tangible constraint on the variety of materials available for planet formation around other stars. More speculatively, certain peculiar emission lines or an unexpected ionization state could even suggest a radically different history of irradiation, perhaps from a stellar flare of unimaginable intensity from a neutron star or a white dwarf, an event that fundamentally altered its surface chemistry in a way never observed within our own solar family. What cataclysmic event, in the deep reaches of interstellar space or in the violent vicinity of its birth star, we could have cooked this object in a furnace of radiation so unique as to produce a chemical composition that stands in such stark contrast to every other body we have ever studied. The implications of a divergent spectrum are, therefore, monumental. It would transform the narrative from a solitary, curious incident to a binary interstellar duet, a rare and precious opportunity to begin mapping the chemical diversity that exists between the stars. 2 data points, while insufficient for a statistical survey, are infinitely more valuable than 1, for they allow us to begin asking comparative questions. They would provide the first direct empirical constraints on the range of chemical conditions within protoplanetary disks, challenging our models of planet formation, which are, for now, overwhelmingly based on a single data point, our own solar system. The very laws of physics and chemistry are universal, but the initial conditions and the specific histories of countless stellar systems are not. These 2 travelers, 3I divided by Atlas and its potentially unrelated companion, would be the first physical evidence of that grand diversity, tangible proof that the galaxy is filled with worlds and worldlets built from recipes we are only beginning to imagine. Yet, if they are so fundamentally different, what does that tell us about the typicality, or the utter strangeness, of our own solar system's formation environment? And as we contemplate the possibility of 2 distinct interstellar visitors, our gaze is inevitably drawn back to the first, to 3I divided by Atlas itself, and we are compelled to look closer, to peer deeper into its immediate vicinity. If it truly is a fragment from a larger body, could there be other, smaller fragments still travelling in its company, hidden from our current view? Could the gravitational pull of this exotic traveller be sufficient to have captured or retained a smaller companion on this epic journey, a silent moonlet orbiting the interstellar wanderer? The detection of such a satellite would irrevocably alter our understanding of the object's nature, mass, and history, transforming it from a simple asteroid into a complex microsystem in its own right. But is such a scenario even feasible? And what would the presence or absence of a small satellite reveal about the violent events that launched 3I divided by Atlas on its solitary path between the stars? Giathwit ve tin no ki quan 3I divided by Atlas kor karthi. The cosmos, in its boundless and silent arithmetic, occasionally deigns to send a messenger from the abyss between stars. These visitors, these interstellar interlopers, are more than mere celestial vagabonds. They are cryptic texts, written in ice and dust, challenging our most fundamental understandings of where we come from and what exists in the great, dark ocean beyond our solar shores. The arrival of 3I divided by Atlas, this second confirmed traveller from another star, presents not just an opportunity, but a profound imperative to read these texts with every tool at our disposal, to interrogate them with a scrutiny reserved for the most universe-altering of possibilities. And as we turn our most powerful eyes toward its anticipated close pass by Mars in the autumn of 2025, one hypothesis, seemingly plucked from the realm of speculative fiction, begins to shimmer with a faint mathematical plausibility: the notion that this solitary voyager might not in fact be travelling alone. The idea of a small satellite, a moonlet, orbiting an interstellar comet, a concept that feels instinctively audacious, a narrative almost too elegant for the chaotic void, is not, upon a closer examination of the cold equations, expressly forbidden. If the gravitational embrace were brief enough, a temporary capture of a fragment in the tumultuous hours or days following a perihelion passage could, in theory, leave a transient companion in its wake. Could the void, so often depicted as empty and lonely, permit such a fleeting dance between two bodies born around another sun? According to current models of cometary physics, the nucleus of a comet is a fragile aggregate, a primordial rubble pile held together by the feeble forces of gravity and the tenacious strength of ancient ices. As these objects plunge toward the inner solar system, the increasing solar radiation begins to sublimate these ices, unleashing violent jets of gas and dust that can act as natural thrusters, spinning up the nucleus and subjecting it to immense torsional stresses. It is within this crucible of stellar heat that comets often reveal their composite nature. The astronomical community has, on numerous occasions, documented the splitting of comets within our own solar system, or the existence of binary and paired populations, where a primary body is accompanied by a smaller, gravitationally bound fragment. These events are not anomalies but rather expected outcomes in the life cycle of a comet, a testament to their inherent structural weakness. The proposed satellite of 3I divided by Atlas could therefore be understood through this entirely conventional lens, a simple cloud of dust and debris, recently ejected from the main nucleus and not yet dispersed by the gentle but persistent push of solar radiation pressure, a transient and ephemeral shroud mimicking the appearance of a cohesive secondary body. Is it not the most parsimonious conclusion to assume we are merely witnessing the ordinary, if dramatic, death throes of a comet? Yet, that explanation, for all its comforting familiarity, fails to account for the unique context of an interstellar object. The processes of aggregation and fragmentation we observe in our own Oort cloud or Kuiper belt occurred over billions of years within a relatively stable gravitational well. An object like 3I divided by Atlas, by contrast, is a survivor of a far more violent genesis, likely ejected from its native system, in a gravitational slingshot of cataclysmic force, an event that would have subjected any loosely bound structure to immediate and total disintegration. The very fact that it has survived its epic journey through the galactic tides and the harsh radiation of interstellar space suggests a core of unexpected resilience, or perhaps a history of formation entirely unlike that of our local comets. This opens the door to a more speculative yet tantalizing hypothesis that what we might be observing is not a recent ejection, but a temporary capture. One could envision a scenario where, during its closest approach to our Sun, the gravitational and non-gravitational forces acting on 3I, divided by Atlas, conspired to tear a moonlet of ice and dust a temporary shard from its surface, a fragment that, for a few brief orbits, achieved a stable, locked phase before the solar wind and tidal forces ultimately blow it away. What if the chaotic birth of this companion is not a sign of its end, but a glimpse into a dynamic process of celestial mechanics operating on timescales so compressed they defy our terrestrial intuition? The opportunity presented by the close Martian encounter in October 2025 is, therefore, unprecedented. It provides a vantage point, a celestial ringside seat from which to observe 3I divided by Atlas, with a resolution hitherto impossible for any interstellar visitor. Our instruments will be trained not merely on the comet itself, but on the space immediately surrounding it, searching for any hint of anomalous motion, any point of light that moves not with the background stars, but in a complex, bound dance with the primary nucleus. The analysis would proceed through a hierarchy of escalating possibilities, each more revolutionary than the last. The first and most prosaic level would confirm the object as a simple, unbound dust cloud, a transient and dissipating halo of particulate matter. The second level would reveal a true temporary capture, a fragment locked in a gravitational waltz for a period of hours or days, a short-lived orbital relationship that would, in itself, provide a stunning laboratory for studying the mechanics of microgravity captures in real time. But it is the third level, the most profound of all, that would send reverberations through the entire field of planetary science. The confirmation of a stable, moonlet configuration, a genuine microsatellite that persists for the entire duration of our observational window. Such a discovery would be a staggering precedent, forcing a fundamental rewrite of our models of comet formation and decay, compelling them to account for new channels of accretion and temporary capture, even within the utterly alien and unforgiving environment of interstellar space. For if such a delicate balance can be struck and maintained by a wanderer between the stars, what does that imply about the prevalence and nature of complex structures in the vast, dark gulfs we once thought to be empty? Yet, to anchor our expectations solely in the quiet ballet of orbital mechanics may be to overlook a more violent, more dramatic genesis for this potential companion. What if its origin lies not in a gentle gravitational capture, but in a cataclysm? The celestial wanderer, a pristine relic from the dawn of our solar system, continues its silent, sunward journey, a voyage of ice and dust measured not in miles but in millennia. To the distant eye of our most powerful observatories, it appears as a singular, tranquil entity, a diffuse glow against the void. Yet, this placid exterior is a grand deception. Beneath the fragile, irradiated crust of its nucleus, forces are gathering, pressures are building, in a slow, cosmic drama that will soon erupt into a fleeting, violent ballet. The trigger is as simple as the turning of a world, and as complex as the physics of volatile ices. A subterranean pocket of frozen carbon dioxide, slumbering in the perpetual night of a subsurface cavity, feels the first touch of sunlight as the comet's rotation brings its hiding place into the dawn. This is no gentle warming, it is a rapid, explosive sublimation, a phase change from solid to gas that occurs in an instant, building up a pressure that the overlying crust can no longer contain. The result is not a volcanic eruption, but a jet-driven explosion, a geyser of vapor and force that punches through the brittle surface, hurling a curtain of pre-existing dust and fresh icy fragments into the waiting vacuum. This is the outburst, a sudden and dramatic brightening of the comet, a signature of its inner turmoil written in light and motion. We have seen such events before, on other comets, their dusty comi blossoming like fleeting flowers in the dark garden of space. But to witness one so close, with such forensic detail, is to be granted a front-row seat to the fundamental processes of cosmic renewal. Could this very mechanism, this explosive breath of a waking giant, be the primary sculptor of the comet's transient atmosphere? According to current models, such outbursts are localized phenomena, akin to steam vents on a planetary scale, where concentrated pockets of highly volatile ices, like CO2 or CO, undergo a rapid transition as they cross the thermal boundary into sunlight. The Hubble Space Telescope, in its decades of vigil, has captured the aftermath of such events on numerous cometary bodies, often describing the resultant dust tail not as a smooth stream, but as a distinct droplet-shaped plume, a morphology perfectly consistent with a single, powerful, and directional ejection event propagating through the tenuous coma. The dynamics are clear. The initial jet of gas accelerates the dust, creating a wavefront, a bow shock of particulate matter that expands and drifts, driven by the gentle but relentless push of solar radiation pressure. The meticulous observation campaign, scheduled for the autumn of 2025, a symphony of coordinated data collection from platforms like NASA's Science and its partners, is designed to capture this very sequence, the initial flash of the outburst, the kinematic lag of the slower-moving dust fragments as they are swept into the developing tail, providing a timestamp of the violence that gave them birth. This is the established narrative, a story written in the equations of fluid dynamics and thermodynamics. But what if the trigger is more nuanced, more rhythmic, than a simple binary transition from dark to light? What if deep within the labyrinthine pores of the nucleus, the CO2 ice possesses a kind of heartbeat, a cyclical pattern of pressurization and release that fires only when the specific angle and intensity of sunlight create a resonant frequency of heating within those cryptic hollow spaces? The initial fragmentation presents itself in a hierarchy of scale, a cascade of disintegration that begins with the smallest of debris. These are the level 1 fragments, countless motes of dust, and tiny agglomerations of ice, no larger than pebbles, liberated by the explosive force. They are the first to be illuminated, creating the initial intense spike in the comet's overall brightness, a flash that alerts our instruments to the event. But their glory is tragically ephemeral. Possessing a high surface area to mass ratio, they are utterly at the mercy of solar radiation. They do not so much drift as they are violently pushed, accelerated to velocities that quickly disperse them into the vastness of the tail, where they rapidly sublimate into nothingness or become lost in the diffuse glow. They are the sparks from a forge, brilliant and doomed. Their brief lives are a direct consequence of the outburst's ferocity, a testament to the sheer power contained within the volatile ices. Yet, their swift demise raises a profound question about the very structure of the cometary nucleus. Does the sheer abundance of these tiny, sacrificial fragments suggest a fundamental weakness, a granular, almost sandy constitution, held together by the faintest of gravitational and cohesive forces, waiting only for a reason to fly apart? Then there are the survivors, the larger pieces that emerge from the dusty maelstrom. These level 2 fragments are the true children of the outburst, shards of the primordial crust and core, some potentially the size of small buildings. They do not flash into existence and vanish. They times emerge asterisk, their trajectories calmer, their fates more complex. Having sufficient mass to resist the immediate, stinging push of radiation pressure, they maintain their brightness for weeks, becoming temporary secondary nuclei within the extended coma. They each develop their own, much fainter, Comean tails, like a family of lesser comets trailing their parent. Their prolonged visibility provides a unique opportunity, a chance to study not just the surface of the comet, but its interior, now freshly exposed to the vacuum and sunlight. They are geological core samples, launched into space for our inspection, but their stability is an illusion, a temporary respite. They are now individual worlds, subject to the same thermal stresses that threatened their progenitor. Could one of these larger fragments, now unburdened from the bulk of the nucleus, undergo its own secondary outburst, creating a cascade of disruption within the main event itself? The most profound and unsettling scenario is that of a cascading fragmentation, a level 3 event. This is not a single rupture, but a chain reaction of disintegration, perhaps initiated by a particularly powerful outburst that structurally weakens the nucleus along fault lines we cannot see. In this narrative, the comet does not merely shed pieces, it begins to systematically unzip. A large fragment breaks away, only to itself fracture days later, its own volatile ices destabilized by the new thermal environment. Then another follows, and another, until the comet's head is not a singular point of car, light, but a train of sizable fragments, a string of pearls stretching along its orbital path, a procession of the dying. This staggered, step-level fragmentation is the ultimate prelude to total dissolution, a slow-motion explosion that could play out over weeks or months. It is a spectacle of both creation and destruction, as the comet meticulously takes itself apart before our eyes. What unseen flaws, what hidden reservoirs of volatile ice must lie within the comet's heart to orchestrate such a complex and protracted final act? With this grand disintegration comes both profound risk and unprecedented opportunity. The violent shattering of the nucleus exponentially increases the population of fine, microscopic dust grains within the coma. For any spacecraft daring to venture close, this presents a significant hazard. A single, high-velocity impact from a nearly invisible grain of silicates could compromise sensitive instrumentation, puncture fuel lines, or disable critical sensors. The environment around a fragmenting comet transforms from a tenuous cloud into a blizzard of potential projectiles, each a silent testament to the violence occurring at the core. Yet, this same chaotic cloud is also a scientific goldmine. This is not the old, processed, and irradiated dust from the surface. This is fresh material, violently excavated from the interior, material that has not seen the sun for 4.5 billion years. Its spectral signature, its chemical composition, is a pristine record of the solar system's birth. The fragmentation, in its terrible beauty, is performing the ultimate sample return mission for us, blasting these precious particles into a volume of space where we can analyze them remotely. We are offered a glimpse into the secret recipe of planetary formation, but at the potential cost of the very tools we use to see. Is the comet's final, generous act of self-destruction also a siren's call, luring our probes into a dangerous, dusty shoal? This delicate balance between risk and revelation forces us to look back, to consult the historical records of other comets, to see if this behavior is an anomaly or part of a grander, repeating pattern. For this particular event does not exist in a vacuum. It is but the latest data point in a long and mysterious sequence of stellar behavior. The clues to its ultimate fate may not lie in its immediate future, but in the archived light of its, and others, tumultuous past. Could this impending outburst be merely one note in a longer, more complex rhythm, a rhythm whose pattern we are only just beginning to discern, and whose origins are deeply intertwined with the very nature of these icy planetesimals? This impending spectacle, however, is not an isolated incident. It echoes with the ghostly signatures of similar events recorded in the annals of astronomy, a pattern of volatile behavior that hints at a deeper, more intrinsic cometary nature. The sudden, brilliant awakening of Comet Holmes, the persistent outbursts of 29P divided by Schwarzmann-Wachmann, and the final, dramatic disintegration of Comet Ison before its solar perihelion. All these historical precedents form a chorus of which our current subject is but the latest voice. The mechanisms may share a common physical basis in volatile sublimation, yet the timing, scale, and progression of these events remain notoriously difficult to predict. They speak to the existence of subsurface structures and volatile reservoirs, whose distribution and stability are still largely unknown. The dense observational coverage planned for this comet provides a unique opportunity to move from simply cataloguing these outbursts to truly understanding their triggering mechanisms. By comparing the light curves, dust morphology, and gas composition of this event with those from the past, we can begin to decipher the specific conditions, the thermal thresholds, the rotational stresses, the internal geology that lead a dormant world to suddenly tear itself apart. The data we gather will not just explain a single explosion, it will test the very models we use to describe the life and death of all comets. But does this comparative analysis reveal a predictable cycle, or does it instead uncover a fundamental chaos at the heart of these icy wanderers, where each comet follows its own unique and ultimately unpredictable path to dissolution? The historical record is not merely a collection of similar events, it is a tapestry of variations on a theme. Consider the Great Comet of 1882, a member of the Kreutz sun grazers, which was observed to break into multiple fragments before plunging into the Sunday. Or the more recent Comet 73P divided by Schwarzmann-Wachmann, which has been undergoing a progressive fragmentation since 1995, offering a slow-motion view of a nucleus in its death throes. Each case presents a different facet of the process. Some comets shatter violently in a single event, others shed pieces gradually over multiple orbits. The key to understanding our current subject may lie in these differences. By analyzing the specific spectral lines of the gases released during its outburst, the ratios of CO2 to H2O, the presence of more exotic volatiles, like ammonia or methanol, and comparing them to the chemical fingerprints of these historical fragmentations, we can begin to classify the nature of the outburst. Is it a shallow, cross-shattering event, or a deep-seated eruption driven by a massive primordial reserve of supervolatile ice? The heartbeat of CO2, we hypothesize, may have a distinct metabolic signature, one that could be matched against the recorded pulses of other comets. This transforms the comet from a solitary object of study into a single specimen in a vast celestial laboratory, a specimen whose dissection will inform our understanding of its entire class. Yet, if these events are so dependent on unique internal structures, can any true classification ever be made, or are we merely documenting the infinite variety of cosmic decay? Furthermore, this comparative approach allows us to probe the ultimate fate of the ejected material. The Level 1 and Level 2 fragments from our current comet will follow dynamical paths dictated by their velocity and solar radiation pressure. By tracking their dispersal and comparing it to the long-term evolution of debris clouds from past fragmenting comets, we can model the creation and dissipation of meteoroid streams. These fragments, ground down to dust, become the seeds for future meteor showers, a final poetic contribution to the Earth's celestial environment. The disintegration of a comet is thus not an end, but a transformation, a recycling of primordial matter into a new, dynamic role within the solar system. The dust that now poses a risk to our probes may, in centuries to come, paint fleeting streaks of light in our night sky. But this grand cycle raises a deeper, more philosophical inquiry. If a comet's death gives birth to new phenomena, can we truly consider it a death at all? Or is it merely another phase in the endless metamorphosis of the cosmos? As we stand on the precipice of this anticipated event, armed with telescopes and theories, we are reminded that we are witnessing a process that is both common and profoundly mysterious. The outburst and its resulting fragmentation are a cosmic spectacle, but they are also a fundamental physical process, a key to understanding the architecture of the smallest building blocks of our planetary system. The contemplated hypotheses, the rhythmic CO2 heartbeat, the hierarchical fragmentation, the historical echoes are not mere speculation. They are a framework for inquiry, a set of questions we will pose to the universe itself when the event unfolds. The comet, in its silent journey, holds the answers. It is a teacher whose lesson is written in fire and ice, a lesson on the forces that build worlds and the forces that tear them asunder. The data we collect will refine our models, challenge our assumptions, and undoubtedly present us with new, deeper mysteries. For in the end, the greatest discovery may not be the confirmation of what we suspect, but the revelation of processes we have not yet even dared to imagine. As we train our instruments on this fragile world of ice and dust, we must ask ourselves, are we prepared for the answers it will give, and for the new, more profound questions those answers will inevitably raise? The silent, perpetual night of the cosmos is not, as we once believed, a realm of immutable stillness. It is a stage for dramas of unimaginable scale and violence, events that unfold over millennia, their scripts written in the language of gravity and radiation. In the hushed data streams flowing from our most powerful observatories, we occasionally intercept a single, dramatic line from this ongoing, play a sudden, brilliant flare against the darkness, an outburst that defies the placid rhythms of the celestial clockwork. The recent emergence of a new, fragmented object in the wake of such an outburst presents us with one such line, a cryptic message that compels us to ask, if a new celestial body awakens in the immediate aftermath of a stellar cataclysm, could we be witnessing, not mere coincidence, but the fundamental cause and effect that governs the life cycles of the most enigmatic inhabitants of the void? From the rational vantage point of modern astrophysics, an outburst is a thermodynamic scream, a violent release of pent-up energy. According to current models, such events can be triggered by a number of prosaic, if spectacular, mechanisms. A comet plunging too close to its star might experience a sudden, explosive sublimation of its volatile ices, casting off a brilliant, ephemeral coma. A dormant asteroid, subjected to the relentless and uneven pressure of solar radiation, might undergo a rotational breakup, its components flying apart in a cloud of dust and debris. The James Webb Space Telescope, with its unparalleled infrared sensitivity, has often been tasked with studying these very phenomena, analyzing the chemical composition of such ejecta to understand the primordial building blocks of solar systems. The official channels of scientific discourse, the press releases from NASA, the bulletins from the European Space Agency, the detailed reports on space.com have meticulously documented these events, framing them within the established paradigms of orbital mechanics and material science. They describe the outburst as the cause, and the subsequent debris as the effect, a closed loop of cosmic causality. Yet, what if the narrative we have constructed is incomplete? The observed sequence, a precise, timed outburst, followed by the clean, deliberate separation of a discrete fragment, possesses an elegance that seems to transcend the chaotic violence of a simple explosion. The data, as passed from the timelines of AP News, NASA Science, and ESA.int, indicate that the object's perihelion in October 2025 was the peak of its activity, a logical time frame, indeed, for an outburst and a subsequent fragmentation. But the sheer specificity of the event, the emergence of a single, coherent shard rather than a diffuse cloud, invites a more audacious thought. Could we be observing not a disintegration, but a propagation? A sequence of rhythmic heartbeats, each powerful pulse ejecting a prepared piece of the whole, a form of interstellar fireworks, where the display is not mere spectacle, but a mechanism of an unknown purpose. The conventional model explains the energy release, but does it truly account for the precision of the fragmentation, the seemingly deliberate act of casting a new traveller onto the cosmic winds? To unravel this mystery, we must consider the evidence not as a single snapshot, but as a sequence of frames in a longer film. The first and most basic level of interpretation is a simple correlation, two events occurring in close temporal proximity. At this level, we acknowledge the conjunction of outburst and fragment, but we cannot, with any scientific rigor, ascribe a direct causal link. It is a clue, a hint of a connection, but it remains circumstantial, vulnerable to the charge of mere chance alignment in the vast chronology of the universe. The coincidence is provocative, but is it conclusive? The second, more compelling level emerges with repetition. Should this pattern outburst, followed by the emergence of a new fragment, followed by a period of quiescent decay repeat itself, the argument for a simple correlation weakens, and the case for a genuine causal relationship strengthens exponentially. A single instance can be dismissed as an anomaly. A second, identical sequence transforms the anomaly into a pattern. It suggests a cyclical process intrinsic to the object's nature, a predictable, if mysterious, life cycle. The very act of repetition implies a stored energy, a structural preparation, and a triggering mechanism that operates on a schedule or in response to a specific threshold. It moves the phenomenon from the realm of random catastrophe into the domain of a regulated, if alien, physiology. And this leads us to the third and most profound level of hypothesis, the possibility of a periodic chain. If these outburst fragment events are not merely repetitive but occur with a detectable rhythm, a predictable cadence, they would whisper of a deep internal clockwork. This would no longer be about surface-level reactions, but about the fundamental thermal and structural architecture of the object's core. It would imply a cycle of energy accumulation and release, a slow, geological-scale charging of a cosmic battery that periodically discharges, not with mindless violence, but with the structured intent of shedding a part of itself. What internal furnace, what subterranean ocean of exotic ices or pressures could power such a relentless, rhythmic pulse across the eons? The practical application of this understanding is as immediate as it is profound. If this model holds, then monitoring for the telltale signature of an outburst becomes our most powerful tool for celestial forecasting. It would grant us the ability to predict the optimal moments for close-range observation, to position our telescopes and probes for that fleeting window when the spectrum is richest with the signals of freshly exposed interior material, untainted by the weathering of space. We would no longer be passive observers of random events, but active participants in a scheduled dialogue with the cosmos. We would be learning to read its pulse. But what external force, what cosmic metronome, could possibly serve as the conductor for this intricate symphony of eruption and birth, guiding the hand that lights the fuse for these interstellar fireworks? For the answer, our gaze must turn inevitably sunward, to the very source of light and life in our system, and contemplate its hidden, more subtle influences. Could it be that the sunlight itself, in ways we are only beginning to fathom, acts as the trigger that initiates the object's enigmatic switch-on cycle, awakening it from its long slumber? It begins not with a roar, but with a whisper of photons, an imperceptible caress from a star. The sun, for all its ferocious power, acts here not as a destroyer but as a switch. A specific, quantifiable flux of its light, travelling for millions of years across the interstellar gulfs, finally arrives at its target, a dark, silent, and seemingly inert wanderer from beyond our ken. This object, known to our catalogues as 3I divided by Atlas, hangs in the void, a testament to the profound cold of the space between stars. Its surface, a complex amalgam of ancient water ice, frozen gases, and dust of unidentifiable provenance, is a palimpsest written by the chemistry of its birth cloud. The initial trickle of solar energy is insufficient to stir it from its slumber. It is merely absorbed, its energy converted into a minuscule amount of heat that is radiated back into the darkness almost as quickly as it is received. The object remains dark, a mere silhouette against the starfield, its existence betrayed only by the patient gaze of our most powerful telescopes tracking its path. But as its hyperbolic trajectory carries it inexorably inward, the flux increases, the whisper becomes a murmur, and the murmur, a command. The temperature at its surface begins a slow, inexorable climb, and deep within its matrix, a threshold is approached. Could it be that this object does not merely react, but awaits a specific, cosmic signal to awaken? According to current models of cometary physics, this initial phase is a straightforward process of sublimation. As solar irradiance increases, the most volatile ices, frozen carbon monoxide, carbon dioxide, and molecular nitrogen, begin their direct transition from solid to gas, creating a tenuous, transient atmosphere, or coma, around the nucleus. This is a well-documented phenomenon, observed in countless comets native to our own solar system. The resulting outgassing can produce a gentle natural propulsion, subtly altering the object's trajectory in ways that allow astronomers to calculate its mass and density. For 3I divided by Atlas, this period was marked by a smooth, predictable increase in brightness, a curve that fit neatly within the parameters of our understanding. The object was behaving as expected, a simple ice ball warming in the light of a foreign sunday. Yet, this conventional explanation rests on the assumption of a homogeneous, reasonably predictable composition. What if the interior structure of this interloper is not a simple mixed conglomerate, but something far more ordered and far more strange? The speculative hypothesis, then, is that we are not witnessing simple sublimation, but the activation of a dormant system. Imagine, if you will, that the surface of 3I divided by Atlas is not a porous crust of random debris, but a sealed shell, a protective layer engineered either by natural processes we have yet to comprehend, or by something else entirely, to withstand the utter cold of interstellar space. The initial, smooth brightening could be a diagnostic phase, a period where the integrity of this shell is tested against the increasing stellar wind. The outgassing we detect may not be from the core, but from superficial ices trapped in the matrix of this outer shield. The object is not yet active, it is merely preparing, its internal clocks and triggers measuring the solar flux with a precision that defies our crude instruments. What unknown chemistry, or perhaps even mechanics, lie dormant beneath that dark crust, awaiting the final, critical command from our sun? The transition from the first level to the second is marked not by a gradual curve, but by a discontinuity, a sudden, brilliant leap in luminosity that defies the smooth predictions of simple thermal models. This is the switch being thrown. The critical threshold is reached not across the entire surface, but at specific, predetermined points. As the temperature at these localized vents surpasses a critical value, perhaps triggering a phase change in a specialized material or breaking a chemical bond that acts as a seal, the shell is breached. The result is not a gentle seepage of gas, but a directed, forceful jet. The sublimation process, once a broad-fronted phenomenon, becomes channeled and focused. These are not random geysers, but precisely positioned thrusters, and their ignition transforms 3I divided by Atlas from a passively drifting body into an object under active, albeit automated, control. The light curve, once so placid, now exhibits a sharp, almost artificial spike, a signature of ignition that echoes more with the firing of a spacecraft's engine than the chaotic outgassing of a comet. Mainstream science would posit that such outbursts are common in solar system comets, often attributed to the sudden exposure of fresh, volatile-rich pockets of ice as overlying layers of dust are blown away. The sudden nature is, in this view, an illusion of scale. What seems instantaneous from our distant vantage point is merely the rapid collapse of a fragile surface structure. The subsequent jets, according to this rationale, are the natural result of gas escaping from the nucleus's interior through weaknesses in its crust, their direction dictated by topography, and nothing more. The observed change in brightness is perfectly explicable by the sudden increase in the surface area of reflective ice and dust, now exposed to sunlight and thrown into the coma. It is a spectacular, yet entirely natural, fireworks display. But does this truly account for the precise timing and the coordinated nature of these events, which seem to correlate so perfectly with the object's passage through specific irradiance thresholds, as if following a pre-written program? This leads to a more profound and more disquieting possibility. The switch phenomenon may be evidence of a state change within the object's very structure. One could hypothesize the existence of an ice sail, a vast ultralight membrane of crystalline water ice or some other metamaterial, folded away within protective compartments. Upon receiving the requisite thermal command, the seals holding this membrane vaporize, allowing it to unfurl, much like the solar sails we ourselves have begun to deploy in experimental missions. The sudden brightening would then be the combined effect of this new, vast reflective surface, catching the sunlight and the violent outgassing used to catalyze its deployment. The object is not just venting, it is configuring itself. It is changing its geometry, and by doing so, it is preparing to interact with its environment in a way that a simple comet never could. What purpose could such a structure serve, and what might its activation tell us about the intentions or the programmed instincts of its sender? The third and most startling level of this activation cycle moves beyond mere brightness and into the realm of motion. With the object now fully active, its fresh, gleaming surfaces and powerful jets interacting with the solar environment, a new force begins to dominate its dynamics: radiation pressure. The relentless, minuscule push of photons streaming from the sun, a force we consider negligible on large, massive bodies, becomes a significant factor on an object engineered to be so lightweight and so reflective. The predicted close perihelion passage in October 2025 is not merely a date for increased activity, it is a crucible, a test of this very principle. Observatories across the inner solar system, from orbiters around Mars to the watchful eyes near Jupiter, are being coordinated into a grand campaign to witness this event. They will not merely watch for a brightening, they will track, with micrometer per second precision, any deviation in the object's path. The anticipated signal is a subtle but definitive nudge, a change in trajectory that cannot be fully accounted for by the messy asymmetric thrust of its gaseous jets alone. The conventional understanding of non-gravitational forces in comets fully includes the Yarkovsky and Yarkovsky-O'Keefe-Radzievsky, Paddock, Yorp effects, where the absorption and re-radiation of sunlight can impart a tiny thrust. For a typical, dark, and rough-surfaced comet nucleus, this effect is tiny, often lost in the noise of much stronger outgassing forces. Scientists would suggest that if 3I divided by Atlas has indeed developed a large, smooth, and highly reflective surface area, perhaps a large fragment of pristine ice, the efficiency of this radiation pressure could be significantly enhanced. The observed deflection, should it occur, would be a fascinating natural experiment in orbital mechanics, providing invaluable data on the material. properties of interstellar objects. It would be a rare opportunity to measure the photon pressure constant on a type of ice-dust composite never before studied, potentially unlocking new designs for future, more efficient light sails for our own vessels. But is the universe in the habit of providing such perfectly tailored natural experiments for our benefit? The more speculative interpretation is that we are not observing a passive object being pushed by sunlight, but an active one, harnessing it. The wings or plumes, captured in our deepest images, are not chaotic jets of dust, but the controlled manipulation of a light-propelled structure. The slight alteration in its course is not a mere physical consequence, but a navigational correction. The object, having used the sun's heat to activate and deploy its systems, is now using the sun's light to sail. It is, in effect, using our star as a slingshot and a power source, a waypoint on a journey whose origin and destination are utterly unknown to us. The coordinated observation campaigns of 2025, then, are not just a scientific study. They are us, a young species, watching an ancient and sophisticated piece of technology execute a complex maneuver in our own backyard. If this is the case, what does that make our sun? Not just a life giver to our world, but a universal charging station and directional beacon for travelers from the abyss? This intricate dance of light, heat, and motion, this three-stage awakening, triggered by our local star, forces us to look closer to home for context. Could the key to understanding this interstellar vagabond lie not in the exotic and the unknown, but in phenomena we have already witnessed, however dimly, within our own celestial family? Consider the transient architecture of our solar system, a dynamic gallery of celestial forms where comets have long been regarded as solitary voyagers, icy sentinels from the outermost reaches. Yet, telescopic surveys such as Pan-STARRS, Atlas, and the Zwicky Transient Facility have meticulously catalogued a curious phenomenon, the binary comet. These are not mere chance alignments, but gravitationally bound pairs, fragile duos of dust and ice tracing elliptical paths through the inner system. The historical archives of the Minor Planet Center and the circulars of the International Astronomical Union reveal that this cometary companionship, while not the dominant form, is a recurrent feature of our cosmic neighborhood. Through the exquisite optics of the Hubble Space Telescope or the Very Large Telescope, the morphology of these pairs is laid bare: twin comas, subtly intertwined tails, a delicate dance orchestrated by gravity's faintest whisper. They present themselves as a single narrative, split into two volumes. If our solar history is punctuated by such ephemeral couples, then the sudden appearance of an interstellar visitor, designated 3I divided by Atlas, invites a profound comparative analysis. Could this lone wanderer from the depths of the galaxy be but one half of a larger, more ancient story? The mainstream scientific explanation posits that binary comets within our solar system are the products of local fragmentation. A progenitor body, stressed by rotational forces or thermal gradients as it approaches the Sun, can cleave itself in two. According to current models, this is a natural consequence of the weak tensile strength of cometary nuclei, a rubble pile of ices and dust, held together by the most tenuous of forces. Scientists suggest this could be due to outgassing torques, or even a gentle collision in the distant past of the Kuiper belt or Oort cloud. The resulting fragments, sharing a nearly identical orbital heritage, would continue their journey as a loosely bound system, their individual outgassing patterns and dust comas creating the illusion of a connected pair in our observations. The light curves of such objects often show a telltale synchronicity, a mirrored response to solar heating that betrays their common origin. But that doesn't account for the peculiar kinematic signatures sometimes observed, the minute deviations in angular velocity, or the persistent phase lag that suggests a relationship more complex than a simple, recent divorce. If fragmentation is so commonplace, why do some of these pairs exhibit a dynamic stability that seems to have weathered eons? This opens the door to a more speculative hypothesis. What if the solar system is not merely a factory for binary comets, but also a gallery for visiting pairs? The interstellar object 3I divided by Atlas, with its hyperbolic trajectory announcing its extrastellar provenance, could be the surviving member of such a celestial partnership. We imagine a scenario where, in the turbulent nursery of a faraway protoplanetary disk, A binary system was born, a interstellar twin set, two nuclei forged from the same primordial cloud and bound by a weak gravitational embrace, destined to wander the galactic plane together. Perhaps their journey through interstellar space, buffeted by galactic tides and close encounters with unseen stars, provided just the right impulse to sever their fragile bond, casting them adrift to enter stellar systems alone, mere fragments of a shared history. Is it not conceivable, then, that 3I is not an orphan, but a twin separated at birth, its counterpart lost to the infinite dark, or yet to be discovered? To move from conjecture toward understanding, we must subject this idea to a rigorous, multi-tiered analytical framework. The first and most superficial level of analysis is that of mere morphology. A telescope image may capture two distinct cometary activations within a single diffuse envelope, suggesting a binary nature. This was the initial clue for many solar system binaries, and it is the easiest to observe. Yet, this level of evidence is circumstantial at best. It confirms a proximity in the sky, but not a physical connection. The human eye is adept at projective the depth, finding patterns, and pareidolia can conjure pairs from random alignments or from the complex, lumpy outgassing of a single irregular nucleus. A similar coma and tail structure could be a mere coincidence of perspective and composition. Can we truly trust a fleeting image to reveal the deep-seated bond between two worlds? This inherent ambiguity necessitates a second, more revealing level of inquiry: the analysis of the photometric light curve. Here, we move beyond static images to the dimension of time. A gravitationally linked binary system will often display a correlated brightness variation. As the components rotate, they present changing cross-sections and active regions to the Sun, and thus to our telescopes. If the two bodies are tidally locked, or their rotations are harmonically related, their individual light curves will echo one another, creating a complex but decipherable signature in the combined data stream. This temporal correlation, this duet of light, is a far stronger indicator of a physical relationship than a simple snapshot. It was through such painstaking photometric analysis that many suspected binaries in our own solar system were confirmed. For an interstellar object like 3I, a detailed light curve could reveal the subtle repeating patterns that hint at a complex, potentially binary structure, or perhaps the ghostly echo of a companion now absent. But does a synchronized dance of light necessarily prove a shared cradle, or could it be a rhythm acquired much later in a long and solitary journey? The third and most definitive level of analysis lies in the realm of dynamics, the precise mathematics of motion. If we can track the relative positions of two suspected components with sufficient precision, we can reconstruct their orbital dance around a common center of mass. The angular velocity, the minute shifts in position, the phase differences in their acceleration due to non-gravitational forces, these are the fingerprints of their gravitational relationship. A model of a binary system with specific masses, separation, and orbital eccentricity can be tested against these exquisite astrometric measurements. A match would be nearly incontrovertible proof of a binary nature. For an object like 3I, such a dynamic confirmation would be revolutionary, but the implications would extend far beyond a simple classification. The specific characteristics of that orbit, its size, its period, the mass ratio of the components, would serve as a fossil record of the conditions of its birth. A loosely bound, wide binary could only have formed in an environment devoid of strong gravitational perturbations, a quiet corner of its protoplanetary disk. The dynamical signature is thus not just a confirmation of a pair, but a Rosetta Stone for interpreting its origin. If 3I were confirmed as one half of a binary, the parameters of its lost orbital dance would provide a unique, calibrated benchmark, a standard of reference utterly alien to our own solar system. How then would the diverse architecture of cometary bodies from our local disk compare to this solitary data point from the galaxy at large? The confirmation of an interstellar binary, or even the strong evidence that 3I was once part of such a system, would fundamentally alter our understanding of planet formation. We would hold in our hands, figuratively speaking, a direct sample of a building block from another star. This would not be a single data point, but a comparative one. We could ask entirely new questions. Is the material strength, inferred from the fact of the binary's survival, similar to that of comets like 67P, divided by Churyumov-Gerasimenko. Is the dust-to-ice ratio, revealed by their activity, comparable? The twin would become a control in the greatest experiment of all, comparing the outcomes of planetary genesis across the galaxy. It would offer a glimpse into the universality or the startling peculiarity of the processes that sculpted our own solar system. The opportunity is nothing less than the chance to perform a celestial autopsy on a system we have never seen, using a fragment that has journeyed across light years to tell its tale. But what if the story is even more complex? What if the object we see is not a primordial twin, but a relic of a more violent past? Liu veithe me, kothe la man verva cham, tu kwaku majeme swethien. In the profound and perpetual silence of the interstellar void, where the temperature hovers but a few degrees above absolute zero, and the passage of time is measured in the slow, patient gyre of the galaxy itself, there exists a repository of cosmic memory. It is a museum of forgotten events. It exhibits the scattered debris of collisions that occurred when the sun was but a youthful star, and its planetary system, a chaotic, violent construction site. The recent appearance of an anomalous object, a transient speck of light and motion, invites us to consider a most patient of narratives, that of a dormant shard, a relic from an ancient impact, which has journeyed for eons in the darkness, only to awaken upon its first touch of solar warmth. According to current models of solar system evolution, the early epochs were characterized by a ferocious bombardment, a period of planetary accretion where planetesimals collided, merged, and shattered with tremendous force. The remnants of this primordial chaos were flung into the distant reservoir we now call the Oort cloud, or into the deep freeze of the scattered disk, where they have resided, preserved in a state of near-perfect stasis. The very structure of comets, as revealed by missions like Rosetta, supports this. Their nuclei are often low-density, porous, and fragile aggregates, essentially cosmic rubble piles, bearing within their structure the potential for harboring the scars of these ancient encounters. It is a scientifically sound proposition that a fragment from Strekjurasting, such a distant event, could have been cast adrift on a long, elliptical orbit, a sleeper agent from the dawn of our system, now returning on a trajectory that finally brings it within the reach of our sun's gravitational and radiative influence. But does the mere possibility of such an origin account for the precise moment of its awakening? The specific trigger that caused this ancient shard to suddenly flare into visibility, as if it were a seed, planted in the deep past, that only now, in the warmth of the inner system, has decided to germinate? The speculative hypothesis, then, is not that such fragments exist, but that they can remain in a state of quiescent hibernation for geological timescales. One might envision this object not merely as a piece of rock and ice, but as a complex structure whose very integrity was compromised in that long-ago collision. It could possess a fractured interior, a labyrinth of cracks and voids sealed by volatile ices that act as a temporary glue, holding the fragile architecture together against the ravages of time. Shielded from significant energy sources in the deep cold of interstellar space, this delicate equilibrium could persist indefinitely. The trigger for its activity would not be gradual heating, but a critical threshold reached as it plunges sunward. The subtle but increasing pressure of solar radiation, the photons themselves, could provide the necessary energy to sublimate the most volatile of these ices, perhaps nitrogen or carbon monoxide deep within its fractured core. This internal pressure buildup would then seek a release, violently expelling dust and gas and effectively causing the fragment to switch on, its dormant potential unleashed in a sudden, brilliant outburst. This would explain the photometric observations of delayed brightening, a phenomenon not entirely consistent with the surface-level sublimation we see in typical comets approaching the sunday. Could it be that we are not witnessing the steady activation of a common comet, but the dramatic awakening of a specific, wounded relic whose internal clock was set billions of years ago and has only now reached its alarm? To comprehend the full implications, we must analyze this hypothesis across a spectrum of scale, beginning with the most ephemeral of events. At the first level, we consider the smallest fragments, mere pebbles or boulders liberated from their larger parent body. When such a minor shard is nudged into the inner solar system, its fate is dictated by the delicate interplay of forces that govern small bodies. The radiation pressure from the Sun, a force negligible for asteroids and planets, becomes a dominant actor on this stage, exerting a constant, photon-driven push known as radiation pressure. For a fragment of low density and high surface area, this force can significantly alter its orbit, a process distinct from the gravitational perturbations that shape the paths of larger objects. As it tumbles sunward, the increasing solar flux would rapidly sublimate any exposed surface ices, causing a brief, intense burst of brightness, a flash in the pan against the dark canvas of space. The released dust and gas would form a transient, faint coma, quickly dispersed and swept back by the solar wind, leaving the now devolatilized rock to fade back into obscurity, a dark and inert testament to its brief moment of activity. This behavior aligns with numerous documented sightings of short-lived cometary outbursts, events that appear and vanish before a detailed composition can be ascertained. But is a brief flash of light truly the signature of a simple, pristine ice sublimating? Or could it be the final, gasping breath of a microscale structure failing under internal stress? A tiny piece of a much larger, older puzzle. Progressing to the second level of analysis, we encounter fragments of a more substantial nature, those on the scale of a small mountain or a large city block. These intermediate objects possess sufficient mass and gravitational cohesion to retain a more complex response to solar heating. Their activation is not a single catastrophic event, but a sustained process. As they cross the frost line, the boundary within which volatile compounds become unstable, the heat penetrates beyond the immediate surface, reaching sealed pockets and layered strata within the body. The resulting outgassing is not a uniform veil, but can manifest as discrete, powerful jets, acting like natural thrusters that can subtly alter the object's rotation and trajectory. These jets carry with them copious amounts of dust, not merely fine particulates but potentially a range of grain sizes, which are then sculpted by solar radiation pressure into a distinct, persistent tail. This is not a transient flash, but a sustained performance that can last for days or even weeks, providing astronomers with a rich dataset of photometric and spectroscopic information. The dust tail, analyzed through its scattering properties, can reveal the composition and size distribution of the ejected material, offering a direct probe into the interior of the fragment, a place otherwise inaccessible. Yet, if this is merely a typical cometary display, why does the spectral signature sometimes reveal mineralogical or isotopic anomalies that do not align with the well-characterized composition of the Kuiper belt or the Oort cloud? Could the sustained brightness and unique dust properties be indicative of a stratified interior, a geological cross-section of a body that was shattered in its youth, exposing layers that have never before been subjected to the heat of a star? The most profound and puzzling level of this hypothesis is revealed when we observe not a single fragment, but a procession, a debris train, of multiple objects traveling in a loose but dynamically related convoy. This is the third level, where the narrative shifts from the fate of a single shard to the reconstruction of a primordial event. The discovery of several fragments on nearly identical or resonant orbits points directly to a common origin in a single, catastrophic disruption. By tracing the orbits of these fragments backwards through time, dynamicists can attempt to run the clock of the solar system in reverse, seeking a convergence point the moment and location of the initial collision. This is a formidable computational challenge, a celestial detective story where the clues are gravitational perturbations from planets, subtle nudges from non-gravitational forces, and the faint pressure of starlight itself. A successful orbital convergence would not only validate the impact hypothesis, but would date it, offering a timestamp from the solar system's deep past. The fragments themselves become a form of genetic code. Their collective physical properties, density, bulk composition, rotational states can tell us about the nature of the parent body and the physics of the impact that destroyed it. Were these pieces of a differentiated protoplanet, its core and mantle scattered to the winds? Or are they siblings from a primitive, unprocessed body, torn apart before it could ever grow? The very existence of such a debris train, surviving the gravitational scattering effects of the giant planets over billions of years, is a dynamical puzzle of the highest order. What chaotic mechanisms, what resonances and safe harbors within the gravitational fabric of our system could have shepherded this fossilized family for so long, preserving their kinship across the abyss of time? The consequences of such a scenario, while not apocalyptic, ripple through our understanding of the local cosmic environment and present unique opportunities. As these fragments, large and small, continue their journey and disintegrate, they contribute to the population of interplanetary dust particles that perpetually rain down on Earth. This would represent a temporary, localized increase in this micrometeoritic flux, a gentle shower of dust grains that were, until very recently, part of an ancient celestial relic. For scientists, this is not a hazard but a windfall. Missions like NASA's Stardust, which successfully captured cometary dust from Comet Wild 2, demonstrated the profound science that can be gleaned from such direct sampling. A future mission, designed to intercept the dust trail of one of these hypothesized ancient fragments, would not be collecting material from a typical comet. It would be, in effect, a robotic archaeological dig, capturing pristine samples from a specific event in the early solar system. These ancient grains could hold isotopic ratios locked in place before the planets fully formed, providing a clearer window into the conditions of the protoplanetary disk than any asteroid or common comet could offer. They would be physical artifacts of a collision that may have shaped the destiny of nascent worlds. But if we were to capture such a grain and analyze it with our most sensitive instruments, would we find the expected primordial signature, or might we uncover something entirely unexpected, a compositional anomaly that challenges our very models of solar system formation? The contemplative narrative of a dormant shard awakening is elegant and compelling, weaving together the known physics of cometary evolution with the grand history of our system's violent birth. It provides a framework to interpret the delayed brightening, the persistent activity, and the potential for fragmented families. Yet, a hypothesis, no matter how poetically satisfying, must face the unforgiving scrutiny of data, the hard light of empirical observation. The initial tantalizing clues from photometric light curves and orbital dynamics have set the stage, but they are merely the prologue. To move from speculative wonder to grounded understanding, we must turn our most powerful eyes to the sky, instruments capable of dissecting the light from these objects across the electromagnetic spectrum, of probing their chemistry and physical state from across the vast gulf of space. The question thus naturally shifts from the realm of dynamical possibility to the domain of spectroscopic confirmation. For if this is truly a messenger from a forgotten collision, then its light must carry the indelible fingerprints of its ancient origin.